Hello everyone. Today's class will learn about directed graph. The graph studied so far was undirected graph, means there was no direction assigned to edges in the graph. Suppose if I say EK is an edge from VI to VJ, if this arrow mark is not there, if it's simply like this, so far we took the graphs which has got such edges without any direction on the edge. So it can be from VI to VJ or VJ to VI, since there was no direction mentioned. If I represent some direction, if I give some direction to the edges, then it must be from VI to VJ. If I give like this, if I give in the reverse order, VI to VJ, then an edge EK is from VJ to VI. So now we'll look at those graphs in which edges have got some directions. So this concept means this directed graphs is used in many physical situations, like drawing a street map of a city with one-way streets, in flow networks, everywhere it is used. Most of the concepts and terminologies of undirected graphs are also applicable to directed graphs. Like for example, if I have a planar graph, it's an undirected graph which is planar. If I put the direction to the edges of this undirected graph, then the graph becomes directed graph. Still the graph will be planar only. There are some properties, there will be some changes with respect to directed graph. So those things I'll mention. So let us learn what is directed graph. A directed graph, or even we say digraph, G, consists of vertex set, say V, vertices V1, V2 like that, and an edge set E, E1, E2 like that, and a mapping chi that maps every edge onto some ordered pair of vertices, say Vi, Vj. For example, if this is my graph, say V1, V2, V3, V4. I'm giving directions to edges, putting arrows. Okay. Now in this, I must say an edge, say E1, is moving from V1 to V2, not V2 to V1. I must say V1 to V2. An edge E2 is from V2 to V3. Edge E3 is from V2 to V4, and edge E4 from V4 to V1. Okay, this is an example, small example I have taken. Remember, this digraph is also known as oriented graph. As in the case of undirected graphs, a vertex is represented by a point, but an edge by a line segment between the vertices Vi and Vj with an arrow from Vi to Vj. Okay, this is how we represent a directed graph. In a directed graph, an edge is not only incident on a vertex. We won't say it's incident on a vertex. We say incident out of a vertex and incident into a vertex. Okay. If I consider this edge, now edge E2 is incident out of vertex V2 and it is incident into vertex V3. I repeat, if I take this edge EK, an edge EK is incident out of Vi and it is incident into vertex Vj. and the vertex Vi from which edge Ek is incident out of is called initial vertex, and the vertex Vj which the edge Ek is incident into is called terminal vertex. So this is the initial vertex and this is the, this is the initial vertex and this is the terminal vertex. You can say for this edge E4, this is the initial vertex, V4 is the initial vertex and V1 is the terminal vertex. So now let us look at few properties. The number of edges incident out of a vertex is called out degree or out valency, and number of edges incident into a vertex is called in degree. Okay. So the first property, the number of edges incident out of a vertex Vi is called out degree of Vi and is denoted by d plus of Vi. The out valency or out degree This is number of edges incident out of a vertex say Vi. That is out valency or out degree and is denoted by d plus Vi. Next is invalence or in degree. This is number of edges incident into a vertex. Vi is called in degree and it is denoted by d of Vi, d minus Vi. Incident into a vertex Vi and is denoted by d minus of Vi. So for the graph, say I'll write the graph. For example, see V1, V2, V3, V4. Now for the vertex V1, d of V1. If I take positive, then it is out degree, means how many edges are incident out of that vertex. For this vertex V1, there are 2 edges which is incident out of it. So it is 2. And in degree is negative. How many edges are incident into that particular vertex? Here there are no such edges, so it's 0. And d plus of V2, there is only one edge which is coming out of V2, so out degree is 1, and in degree this is only one edge which is coming to V2, therefore the in degree is also 1. Out degree for the vertex V3, there is no edges which is coming out of V3, therefore this is 0, and in degree is 2. There are 2 edges which is incident on V3, and similarly out degree for V4 is 1 and in degree is also 1. can check one thing. When I sum up all the out degrees, that is equal to sum of all in degrees. It's quite difficult to prove theoretically, but we can say summation of in degrees is equal to sum of all out degrees for a particular vertex. In fact, it is equal to the number of edges in the directed graph. Next thing, if I have an isolated vertex, for an isolated vertex, in degree is equal to out degree, and that is equal to 0. This is in case of digraph. For an isolated vertex, in degree is equal to out degree, which is equal to 0. And if I have a vertex in digraph, if it is a pendant vertex, then what happens to its degrees, in degrees and out degrees? Pendant vertex, for the pendant vertex, in degree plus out degree is equal to 1. If the vertex is pendant vertex in the directed graph, then its in degree plus its out degree is equal, this is I only, degree is equal to 1. You can say, so you can check it. If this is my graph, this is the pendant vertex, okay. It has got some direction now. So this is the pendant vertex, there is only an edge coming to this. There are no edges going out of it, of course. Therefore, its in degree is 1 and out there is no degree, that is 0. So sum is always 1. Okay, so I can say a vertex in the directed graph is pendant vertex if this is true. Means it's of degree 1. Then what happens to the parallel edges? When I can say that my directed graph has a parallel edge. Two edges are said to be parallel if they are mapped onto same set of vertices and its directions are same. Means if I have an edge over here, even if this has got like this direction, then only I can say that these two are parallel. Like these two are parallel. But when I consider these two edges, they look parallel but they are not because of their directions. Okay, these two are not parallel but these are parallel. That is same as saying edges are parallel in the sense of undirected graphs, and also the parallel edges agree with the directions. Then I can say that edges in the directed graph are parallel. So when I look at here, these three are parallel but these two are not parallel. Next is type of graph. Simple digraph. Next is, we say simple graph, that is graph with no self loops and no parallel edges. Similarly, simple digraph is a graph with no self loops and no parallel edges. One more type of digraph, that is asymmetric digraph. It's a digraph that have at most one directed edge between a pair of vertices but are allowed to have the self loops. Okay, there are no edges like between the pair of vertices. There can be only one directed edge and it can have self loops. Such graphs are called asymmetric digraphs. Next is symmetric digraph. If there is an edge between from A to B, then there has to be an edge from B to A, and it is true for all A, B, means all the vertices in the graph. Then such graphs are called symmetric graphs. Means if I have an edge from V1 to V2, then there has to be an edge from V2 to V1. And if all the set of vertices have such edges, then I can say that graph is symmetric. A digraph in which for every vertices for every set of vertices v1 to v2, there has to be an edge from v2 to v1. Then I can say that graph is symmetric. This is an example for symmetric graph. A digraph which is both simple and symmetric is called simple symmetric digraph, and the digraph which is both simple and asymmetric is called simple asymmetric digraph. Remember, in case of asymmetric digraph, see, there is an edge from this vertex to this vertex. I cannot have an edge like this. Okay, since I know they are not parallel, but this is not allowed. Okay, at most one directed edge between a pair of vertices. Okay, this thing is very much important. Okay, let us look into one more type of digraph, that is complete digraph. A complete undirected graph is defined as a simple graph in which every vertex is joined to every other vertex exactly by an edge. Okay, only one edge. But when I take complete digraph, I look into complete symmetric digraph and a complete asymmetric digraph. Okay, first is complete symmetric digraph is a simple digraph in which there is exactly one edge directed from each vertex to every other vertex. For example, say if this is, it says there is exactly one edge directed from each vertex to every other vertex. Okay, now when I consider v1 to v2, there is a directed edge from v1 to v2, but there is no edge from v2 to v1. So to make it complete symmetric, I am drawing it like this. Now from v2 to v3 there is an edge, from v3 to v2 also there has to be an edge. Similarly, from v3 to v1 there is an edge. From v1 to v3 there has to be an edge, so that I can say that this is complete symmetric digraph. It's a simple digraph in which there is exactly one edge directed from each vertex to every other vertex. But when I write complete asymmetric digraph, is also a simple digraph, but in this case there is an exactly one edge between a pair of vertices. See, I'll take the same graph, okay, graph on 3 vertices. This says simple graph, no parallel edges and no self loops, but there is exactly one edge between every pair of vertices. Between every pair of vertices there is an edge. It's not necessary to have an edge from v2 to v1 like that. If there is only one edge, exactly one edge between every pair of vertices, then the graph becomes complete asymmetric digraph. In case of symmetric digraph, there has to be directed edge between every pair of vertices. Thing to remember is a complete asymmetric digraph with n vertices. If I say this is nothing but simple graph only, in fact there is no parallel edges and no self loops, but the thing is this should not have any isolated vertex. Okay, that you have to remember. So a complete asymmetric digraph with n vertices contains n number of vertices, contains n into n minus 1 by 2 edges. but a complete symmetric digraph on n vertices if I consider, then it has got n into n minus 1 edges. And this complete asymmetric digraph is also called a tournament. It's also called a tournament, or even we say complete tournament. And a digraph is said to be balanced if for every vertex vi, in degree is equal to out degree. One more point to remember, we can say digraph is balanced if for all vi in degree is equal to out degree, then I can say that graph is balanced, digraph is balanced.